Okay, so this video is all about vectors, which we introduced in the previous video. We need to know how to add up vectors when there's more than one vector involved in a situation. For example, here in this picture, you've got several different guys all pulling on this rope, right, in order to try to move that rock. So you've got a force by this guy, you've got a force that's acting by this guy, and you've got at least one more guy here, and possibly more. All of them are pulling on the same rope, and all of them are pulling in the same direction. So each of them is a vector, is the force they're putting on this rope is a vector, and the force this guy's putting on the rope is another vector. So we want to know, how does that all add up? All right, so there are a couple different situations involved when we have vectors. One situation is like this one here, pulling in a straight line, for example. All right, so when the vectors act in a straight line, all right, so the vectors here are acting in a straight line, then all we need to do really is, I've written it off to the side here as text, you add the magnitudes of the two or more vectors, all right, together, and that gives you the resultant vector, which acts in the same direction as each of the components, if they're all pulling in the same direction. All right, so if you have an example like this, you simply add up all the vectors. All right, there's several guys here, you add up all the vectors, they're all pulling the same direction, so just add them up. Add up the magnitudes, and then the magnitude of the resultant vector is going to be the same direction. Cool. Now sometimes you're going to have the vectors acting in a straight line with each other, but in opposite directions. So in this case, remember, vectors have both a magnitude and a direction, so we would define one of these two directions in this tug-of-war contest as being plus, and the other one is a minus. So according to convention, plus goes in the same direction as if this was a coordinate axis, right? If this is an x-axis, then plus is that way. So by convention, the plus would be on this side, and the minus would be on that side. So typically that's how you'll see this in problems like this one, okay? So what we have here is a vector in the minus direction, and we have a vector in the plus direction. Now probably you can tell that one of those two vectors is longer than the other one, and it's this one. That one's longer, okay? So how do we add up these vectors to find out the resultant? Well, same as the previous one, we add the two vectors, but since one of them is negative and the other one is positive, the resultant is going to be the difference between the two, all right? And the resultant vector will act in the same direction as the larger of the two vectors, so that's going to be this one, all right? So in this case, let me just zoom out again. In this case, the resultant vector will be something small, but it's going to be going that way, right? That way. So not very big, but it's acting in that direction, and it will be a negative, right? So negative vector acting in the direction that I've just shown right there. Cool. Now here is where we get complicated. This is the second type of situation, all right? We have pulling in two different directions, not in a straight line. They're at an angle. They're acting at an angle from each other. So the example I decided to show you here is two trucks, all right? And they're both pulling on some random object. It doesn't matter what this object is, but they're both hooked up with ropes and they're towing this object. The question is, what is the resultant of these two vectors? You've got a vector going that way and you've got a vector going that way. We're told that the angle between them is 100 degrees. Right there, that angle, 100 degrees. All right, so what is the resultant vector is the question. So the resultant is going to be somewhere between them, probably more toward this one because it's pulling harder. But we don't know for sure. We have to calculate it out. Although we don't actually use equations for this, we have to use our ruler, our protractor, and scale drawing and that kind of stuff to do this, okay? So I'm going to go through that whole process in the next few slides, all right? So we're told that this truck pulls with 2,000 newtons, this truck pulls with 4,000 newtons. So here's step one of this process of finding the resultant vector. Okay, step one, redraw the diagram properly to scale using a ruler, protractor, and preferably on graph paper. You also need to choose a scale for your drawing. For example, in my drawing here, when I was looking at the computer screen, I made my scale, as I was measuring it on the screen, I made the scale to be 400 newtons equals 1 centimeter. All right? So that means that the 2,000 newton vector here was 5 centimeters on my computer screen. And that also means the 4,000 newton vector was 10 centimeters on my computer screen. The angle here, which I measured with my protractor, is as close as I could make it to 100 degrees. All right? So that is the first and second step. Redraw the diagram properly to scale using your chosen scale. All right, sorry about that. Using your chosen scale. All right? So you have to make a scale that will fit on your paper, which is an important thing. So the next step. All right, so step 3 is to create a parallelogram, finish a parallelogram using the 2 original vectors there as 2 sides of the parallelogram, okay? Now you need to, so we're going to make a parallelogram. It's basically a 4-sided object where the opposite sides are parallel to each other. So this one is parallel and equal to that one. This one is parallel and it's equal in length to that one. The couple things you need to remember about a parallelogram is that opposite angles, opposite interior angles, so this angle and that angle are equal. So this angle is 100 degrees, this angle is also 100 degrees. The other thing that's important when you're drawing the parallelogram is that this angle here plus this angle have to add up to 180 degrees. So angles that are adjacent to each other, this one and this one for example, or this one and this one, they have to add up to 180. So you can see I marked here that this is 80 degrees because if this is 100 then, and the two of them have to add up to 180, then 100 plus 80 is 180 degrees. All right? So this is 80 degrees, this is 80 degrees, 100 degrees, 100 degrees. This is a side that's equal to 4,000 newtons. This side is also equal to 4,000 newtons. Opposite sides are equal. All right? Opposite angles are equal, and then the adjacent angles have to add up to 180 degrees. All right? All right, step 4 is that you're going to draw the diagonal of the parallelogram, starting at the corner right here, your original corner of the parallelogram, and then you go into the opposite corner. So basically you start from the base of your vector, which is the tail, if you will, and then you're going to go to the head of the vectors. This is the heads right here. Okay? So, and then, as you can see the way I drew this, these are also heads here. So, you go from the tail down to the head. Okay? Alright, so this is step 4. I hope you're following along here. Keep in mind, I did all of this as much to scale as I could. As you do these kinds of problems yourself, you're going to have to do it on paper. You're going to be using your ruler to make sure you get all of these measurements exactly correct for the scale that you've chosen, and all of these angles exactly correct using your protractor. Okay? The closer you can get these to exactly correct, the closer you get to the correct answer. Alright? So this is this step. And then the final step is that you need to now measure the resultant vector. Okay, so you measure the angle from one of the sorry, let me back up, I missed a step here. There we go. Okay, so you're going to measure the resultant vector and see how long it is. And then you use your scale to convert that back into the correct units. All right. So if you remember, this was forces. The unit of force is newtons. So if you recall, this side was 4,000 newtons, this side was 2,000 newtons. We got out our ruler, we measured this resultant vector, and I discovered that it's actually not much longer than this one. It was about 10.5 centimeters. If I use my scale then to convert that, I've done it over here. Alright, about 10.5 centimeters long. If I use my scale to convert that, I come up with 4,200 newtons is the value of that. Just recall, basically, 10.5 centimeters times 400 newtons gives me 4,200 newtons. Cool. Alright, so we know then the size of the resultant vector. Now we need to be able to report its direction. Okay, because remember, vectors have to have a direction. Okay, and you can't just say like, well, it's going kind of sideways. You know what I mean? We need to be able to give a number to that as often as we can. So in this case, we're going to report it as the angle away from this 4,000 Newton vector. All right, so I measured that angle right in there. I came up with 28 degrees. So essentially, we would say as our answer, the resultant vector is 4,200 newtons in magnitude, acting at an angle of 28 degrees away from the truck that is pulling with 4,000 newtons of force. Okay, so if we refer back, or if we think back to our original picture of two trucks pulling on something, then you've got the one truck pulling this direction, you've got the other truck pulling that direction, and the result is that the object would move in this pathway right here, that direction. Okay, I hope that was clear. This is a topic that some students have a lot of trouble understanding. So now with this video at your disposal, I hope you'll be able to go back and re-watch this as often as you need to in order to make sure you understand how this process works. Now granted, I'm not doing this on paper here, but if you were doing it on paper, the process is exactly the same. Graph paper is very helpful for this because it lets you keep track of your angles a little better, and it lets you keep track of your measurements a little easier. So I recommend graph paper for this. Another thing that's worth noting is that the orientation of your diagram here often is not going to matter very much. You can switch the orientation however you want on your paper to make it easier to work with. You just have to remember in the end that when you report the direction of the resultant vector, it needs to be in reference to the original orientation of the picture. Okay? All right. Hope that was clear. And we'll be working with this in class.